Good evening, everyone. My name is Vikrant. So very good evening to all of you. My name is Vikrant Narang, and on behalf of Space India, it is my great pleasure to welcome all of our students and budding astronomers to Ask an Astronomer, where you get to ask your questions to professional astronomers. My name is Vikrant. So very good evening professional to astronomers. My name is Vikrant Narang, and on behalf of Space India. So, where you get to ask all your questions to a professional astronomer. Thank you for Vikrant. So, very good evening to all of you. Sorry for. My name is Vikrant Narang, and on behalf of Space India, it is my great pleasure to welcome. Okay, sorry for the echo. So. To all of you, my name is Vikrant Narang, and on behalf of Space India, it is my great pleasure to welcome all our students and budding astronomers to Ask an Astronomer, where you get to ask your questions to a professional astronomer. Thank you all for joining today. Today's topic is imaging of the Sagittarius A star, the supermassive black hole at the center of our own Milky Way galaxy. It is my great honor to introduce all of you to on behalf of Space India. I welcome Dr. Patrick Das Gupta, who is our guest astronomer of the month. Dr. Patrick Das, so welcome Dr. Patrick Das Gupta.
Thank you very much, Vikrant.
And Dr. Patrick Das Gupta is a professor of physics and astrophysics at the University of Delhi. He, along with his late wife, Dr. Ratnashri, the former director of Nehru Planetarium, New Delhi, have been a great source of inspiration for the work we do at Space India. I thank Dr. Patrick Das Gupta, sir, for taking out his precious time today to come and answer all your queries. He got interested in astronomy when he watched the first astronauts land on the moon, and later when India launched its satellite Aryabhat. Dr. Patrick Das Gupta has been giving several lectures on astronomy to inspire public into science. Dr. Patrick Das Gupta did his master's MSc in physics from Birla Institute of Technology and Science, BITS Pilani, in 1981. After this, he completed his PhD from Tata Institute of Fundamental Research in Mumbai in 1989, along with Professor Jayant Narlikar. He joined Delhi University as a lecturer in 1993 and has been working as a full-time professor at the Delhi University since 2004. So thank you once again to Dr. Patrick Das Gupta for taking out his precious time today. We thank all the students for sending your questions in advance, which we will be asking to Dr. Patrick Das Gupta, sir. And so sir will be now sharing his short presentation on the topic, after which we will have Q&A. We have received the questions in advance, and please feel free to ask your questions in the YouTube also. So without further ado, the mic is over to Dr. Patrick Das Gupta.
Am I audible?
Yes, sir.
And is the screen visible?
Yes, sir. Just that.
Now I will go into the slideshow mode.
Okay.
Is the full screen mode visible?
Very much, sir. Yeah.
Okay. So just as a starter, I'm going to remind you all that in 2020, the Nobel Prize was shared by the theoretical physicist Professor Roger Penrose and two astronomers, Professor Andrea Ghez and Professor Reinhard Genzel. And this Nobel Prize was given for the work on black holes. Professor Roger Penrose, in a seminal paper published in 1965, he showed that all standard matter, when they collapse gravitationally, there is sufficient amount of mass, then formation of a singularity is inevitable. This is the first of the singularity theorem that was initiated by Professor Roger Penrose. On the other hand, Professor Andrea Ghez and independently Professor Reinhard Genzel, they studied the motion of stars around Sagittarius A star and gave strong evidence to support that the center of our Milky Way indeed has a supermassive black hole. Now, one should also pay tribute to some of our own Indian theoretical astrophysicists and general relativists. First, we have here Subramanian Chandrasekhar, but for his work on white dwarf, for which he, of course, was given Nobel Prize in 1983, one would have thought that black holes are only interesting mathematical solutions. What Chandrasekhar showed is that given the core of a star to be more massive than a particular threshold, the collapse to a black hole is inevitable. While late Professor A.K. Rai Chaudhuri, who in 1955 published an epoch-making paper in which, from general theory of relativity, he wrote down an equation involving the focusing of null geodesics and other time-like geodesics in the presence of matter, shear, rotation, and so on. This Rai-Chaudhuri equation, because of its seminal importance, all general relativists, they call this equation in honor of Professor Rai-Chaudhuri as Rai-Chaudhuri equation. And this Rai-Chaudhuri equation was used as far as null geodesics are concerned by Professor Roger Penrose to prove the singularity theorem. Later on, of course, Stephen Hawking, along with Roger Penrose, they continued a series of papers on singularity theorem, and all of these papers essentially hinged on Rai-Chaudhuri equation. Now, what did Professor Andrea Ghez and Professor Reinhard Genzel, what did they do? What essentially they studied independently. Professor Genzel is from Germany and Professor Andrea Ghez is from USA. They independently, in real time, they monitored the motion of stars around this asterisk. This asterisk is the so-called Sagittarius A star. This is located at the center of our galaxy. So our Milky Way galaxy, this is an artist's conception of our Milky Way galaxy. And our solar system is about 27,000 light years from the center of the galaxy. And at this center, there is a massive object, but how compact is the massive object? And that is what was studied by Professor Andrea Genzel and Professor Professor Andrea Ghez and Professor Reinhard Genzel. And they showed that the stars, as they move around this point, they suddenly turn around, and such an orbit is extremely eccentric elliptical orbit, and from the distance, closest distance of approach, you can find out how close a star can go to this center. And if you have a circular orbit, then you can easily estimate what is the mass at this point. How do you do it? Simple school level idea. If an object is going in a circular orbit around this central point, and if its speed is v, then the centripetal acceleration will be v squared by r, and this centripetal acceleration will be provided by the gravitational pull of this mass at this point. So v squared by r will be equal to gm by r square, because gm by r square will be the gravitational acceleration due to a mass m here, and v squared by r is the centripetal acceleration. So r. Now v you can estimate by the total time it has taken to go in a orbit plus the radius. So if you know the distance of the Milky Way center and your telescope can find this angular distance, then one can measure the r. So radius of the circular orbit can be found out from the observation, real-time observation of the circular orbit motion. So v is known, r is known, and from this equation you can estimate the mass. And from their estimate, the mass turned out to be something like 4.5 million solar masses. As we know, Sun's mass is 2 into 10 to the power 33 gram, and this object was about as determined by both the group, by Guess group from USA and the German group, namely Professor Genzel's group. They estimated the mass to be 4.5 million solar masses. And how close did one of the stars go? The closest approach took place around 2018 on 19th May, and this distance was only about 120 times the Earth-Sun distance. As you know, Earth-Sun distance is called the 1 astronomical unit, and its value is about 1 times 10 to the power 13 centimeter. So in other words, this distance was only 20 billion kilometers. So if you have a mass of the order of 4.5 million solar masses and its size is less than 20 billion kilometers, then only astrophysical object that can have a radius less than 20 billion kilometers and mass of 4.5 million solar mass can only be a black hole. So what Professor Gaze and Professor Genzel showed from the stellar motion indirectly was that you have a massive, very massive object whose size is less than 20 billion kilometers. All right. Now we'll come back to this point. Now our Milky Way galaxy is a spiral galaxy. This is a typical spiral galaxy, which happens to pose to us face on. So Milky Way, you can't of course see Milky Way in the following manner, because you have to go out of the Milky Way's disk to see such an splendid view of Milky Way. But this is another galaxy. This I have just shown to tell you what kind of a galaxy or Milky Way is. So you have a Milky Way galaxy with the central region and spiral arms where newly born stars are forming. But there are other kinds of galaxies. This is an elliptical galaxy. This is the famous elliptical galaxy M87. The center of M87 also has a black hole, but this black hole mass is much, much bigger than the black hole at the Sagittarius A star. The M87 supermassive black hole is about 6.6 billion solar masses. That means it's heavier than, it is about 6.6 billion times heavier than the sun, our sun. And you can see in this picture, optical picture of the M87 Milky Way galaxy, there's a jet-like feature coming out. So this jet is because of all matter swirling around a supermassive black hole. So as you know, this was the Event Horizon Telescope image of the photon sphere around the supermassive black hole at M87. So what you see here, so this is the event horizon size. What you see here is radiation. After all, the black hole itself cannot be seen at classical limit because black hole by itself will be dark. But what you are seeing here is that matter which is going around the event horizon, they radiate photons, and these are the photons from the matter going around the M87 supermassive black hole. And as you can see, here there is radiation, but here there is nothing. And this nothing is what is enclosed by the event horizon of the supermassive black hole. Now, let me give you an intuitive and Newtonian way of understanding what a black hole is. By the way, this was originally given in the 18th century by Michel from UK and Laplace from France. What they argued was that if you have a star of mass m and radius r, then you can calculate what is the escape velocity from the surface of the star. How do you calculate? You know that if something has to barely escape to infinity, at infinity, its velocity must be zero. And at infinity, its gravitational potential energy is also zero. But on the surface, its energy is half mv squared minus the gravitational potential energy, gmm by r. Capital M is the mass of the star. Small m is the mass of the object that you are throwing with the escape velocity v. So, since energy is conserved, if this object escapes to infinity, its total energy is zero, because barely if it is at infinity without any motion, its kinetic energy is zero at infinity, and at potential energy is also at zero at infinity. Energy is conserved, so if you're throwing from the surface of the star, kinetic energy is half mv squared, potential energy is minus gmm by r. From this, you immediately see that the solution is that the escape velocity v is square root of 2 gm by r. What Michel and independently Laplace argued is the following, that suppose this object starts shrinking. If the star shrinks to a radius 2 gm by c square. So if you put for this mass the value 2 gm by c square, okay, immediately here in this radius, if you put 2 gm by c square, you will find the escape velocity to be equal to c. In other words, if the star contracts to a radius 2 gm by c square, then the escape velocity happens to be the speed of light. And if the star contracts further, the escape velocity becomes greater than the speed of light. So what they argue is that if a star is contracting, if it contracts below the radius 2 gm by c square, then even light can't escape from the surface of the star. So even from the Newtonian perspective, and knowing from special relativity that nothing can move faster than the speed of light, we can immediately see that any spherical object, if it has a mass capital M and radius less than 2 gm by c square, nothing can escape from the surface of the object, and it has become a black hole. So in other words, of course, black hole truly speaking, comes as a solution from Einstein's general theory of relativity. So later on, if you study general relativity, you will understand why black holes become inevitable. But the first solution which led to the notion of black hole was by Carl Schwarzschild. Carl Schwarzschild, as soon as general relativity was published in 1915, Carl Schwarzschild got a copy of Einstein's paper and he worked out an exact solution from the difficult mathematical equations of general relativity. And from that, what could be seen is that if a spherically symmetric object having mass m, if its size becomes less than 2 gm by c square, exactly like what Michel and Laplace had argued, then the entire mass will keep on shrinking to a single point. So according to general relativity, if the mass becomes less than 2 gm by c square, then the entire matter will fall into a single point. So therefore, the matter density at that point becomes infinity. And from general relativity, one can show that the space-time curvature becomes also infinity at this point. Now, this radius, 2 gm by c square, as a respect to Carl Schwarzschild, is called Schwarzschild radius. So the Schwarzschild radius Rs for a spherically symmetric black hole is 2 gm by c square. And because the Schwarzschild radius, which is the radius of the event horizon, is proportional to the mass, it scales linearly as the mass of the black hole, you can numerically compute, and Schwarzschild radius of any object of mass m is nothing but m divided by sun's mass times 3 kilometers. So if the mass of the black hole is twice the mass of the sun, then it will be 6 kilometers. 6 kilometers will be the Schwarzschild radius, or which is the size of the event horizon. While like the M87 supermassive black hole, if m is 6.6 billion solar mass, then 6.6 into 3, which is, about 19.8 billion kilometers. That will be the Schwarzschild radius of the M87 black hole. While for Sagittarius A star black hole, if you put 4.5 or 4, let's put 4 million solar mass here. So it will be 3 into 4, which is 12 million kilometers. So it will become 12 million kilometers. And note, the original star picture that I had shown, the closest approach, if we go back, was 20 billion kilometers, much, much, much far away from the event horizon of the Sagittarius A star black hole. So what I said right now is that the event horizon size of the, if you assume it to be Schwarzschild black hole, our simple calculation tells us that the event horizon size is about 12 million kilometers, while the star that was orbiting close to the Sagittarius A star black hole had approached 20 billion kilometers, much, much far away from the event horizon of the Sagittarius black hole. So the event horizon can be, this is an analogy, don't take the analogy too seriously. Why you can't escape once you go below the event horizon is like this waterfall analogy. Imagine that there is a river stream which ends up into a waterfall. So because this is a slopy stream, the velocity of the river keeps on increasing as you go towards the edge of the precipice. Now, supposing I am riding a boat, okay? Now, let's say compared to water at still, I can at the most row the boat with a velocity v boat. That's the limit, okay? With respect to still water, remember that. So if the water is at rest, the fastest I can move with respect to still water is v boat. Now, this dotted line is the line at which the reverse velocity towards this direction is v boat. Now you can immediately realize the reverse velocity here is lesser than v boat, here it is greater than v boat. But suppose I am here rowing my boat, I can always go back, okay, because here the velocity of the river in this direction is less than v boat. So therefore, if I am rowing with v boat in this direction, the velocity will be with respect to the stationary observer, the bank, will be v boat minus v river. V boat minus v river will be positive in this direction. But once I cross this dotted line, that's it. I cannot return. I cannot go in this direction. Once I cross this dotted line, now the velocity of the river in this direction is greater than v boat. So in this direction, my velocity will be v boat minus v river. Now it is negative 1. So therefore, I'll be drawn inexorably towards the edge of the precipice, and I will simply fall along with the waterfall. So this dotted line is like the event horizon. This is just an analogy. Let's not go into the mathematics. Let's not go into all this mathematics. Now, of course, what today we will discuss is the latest image which has been shown by the EHT, Event Horizon Telescope, about the black hole at the Sagittarius A star. Again, you see the matter is swirling around the black hole. This part is dark. So this part is the region of the event horizon. And again, you see that there is nothing here. So it is again an indirectly showing that indeed there is a supermassive black hole at Sagittarius A star. Now, let me also show that what exactly is, so this is the optical image towards the Sagittarius A star or Milky Way. And if you even use a X-ray telescope, Chandra X-ray image of the central region of the Sagittarius A star, you see this emission. There is X-ray emission, and toward the center, the X-ray intensity goes up. So you might ask that all this Chandra telescope is revealing is there is a lot of X-ray emission happening from the core of the Sagittarius A star. You might ask, if there's a black hole, where is the X-ray emission coming from? This is really due to the matter swirling around the black hole. So there are many such cases like quasar, where from the region around the black hole, you see powerful radiation coming. So this is in fact a Hubble Space Telescope of a radio galaxy which is elliptical otherwise, but in radio, you can see jets, and the core of this radio galaxy with the Hubble Space Telescope, again, you see this image, and this is the accretion disk around the supermassive black hole of the elliptical galaxy NGC 4261. While this is the M87, this is the M87 elliptical galaxy from where you see jet, and at the very center you have a supermassive black hole. You might ask, why would matter emit radiation when it is going around a black hole? So again, the thing is, when matter is going around a supermassive black hole, as it falls towards the event horizon, its kinetic energy keeps going up, because from far when it falls, the gravitational potential energy minus GMM by R. As R becomes smaller and smaller, the gravitational potential energy becomes more and more negative, and energy is conserved. So kinetic energy has to become larger and larger. So therefore, the matter which is near the event horizon, it's going very fast. So therefore, there is an accretion disk formed around the event horizon. This matter, as it falls toward the event horizon, is going faster, is colliding with other particles, becomes so hot that it starts emitting X-rays, because the kinetic energy towards the event horizon. So here is a black hole, here's the event horizon, and matter from far away, as it falls, its velocity keeps increasing. The other matter is falling from another side. The velocity is increasing. They collide with each other with great velocity, and they become very, very hot. And you have a hot disk forming around the event horizon, and it's this hot disk that emits the X-rays. And if you have magnetic field, and if the rate of matter accretion is very high, then you have a very, very luminous accretion disk, and the magnetic field collimates plasma jets, and you can have radio jets like features. So, in other words, this is a cartoon of what happens inside of an atom. Plasma accretion disk around the event horizon. The warp magnetic field, they collimate matter, plasma matter, into relativistic jet going out. It is this jets which appear as radio jets. And for M87, of course, the jet shows up also in optical, X-rays, and gamma rays, and so on. So ultimately, it is that is what shows up as radiation. If the rate of matter accreting is not very high, then the object won't be an active galactic nuclei. So, for example, our Sagittarius A star, there the rate of matter that is infalling near the event horizon, that's not very high. And that's the reason why Sagittarius A star is not a bright object like a quasar or M87 radio galaxy and so on. Okay, so this is a graph. I mean, maybe when there is question answers, we will talk about it. There's a in the y-axis you have plotted luminosity. In the x-axis, the inferred black hole mass. As you can see, one of the quasars, J0100 plus 2802, is a very bright quasar. Its luminosity is more than 10 raised to power 14.6 times the sun's luminosity, and the inferred black hole mass is more than 10 billion solar mass. Okay. There is now another black hole, supermassive black hole has been, quasar has been discovered, called Titan. There, the supermassive black hole mass is even bigger than 12 billion solar mass. This is about 12 billion solar mass, while the Titan quasar, or sorry, not Titan, TUN, this TUN 618, TUN 618 has a much, much bigger supermassive black hole. Okay, maybe if there are questions, I will talk about it. I think we should start having questions. Otherwise, it would become end up as a monologue. More important that we have as many questions as the time permits.
Okay, thank you, sir, for such an enlightening presentation, such a gripping presentation. So we have lots of questions, and so first of all, Sanskriti is asking, actually one of the students is asking, not Sanskriti, she's asking, is there a lifespan of a black hole?
Very good question. So classically, if you take general relativity alone into account, then black hole can horizon is like a one-way traffic surface. So the matter will just fall and black hole mass will grow. Okay. So if general relativity is to be taken into account only, then a black hole mass can only grow. But in 1974, Stephen Hawking, what he did was he showed by taking quantum theory near the event horizon of a black hole, he showed that if you take into account quantum mechanics of matter near the event horizon of a black hole, there are these virtual pairs created because of vacuum fluctuation, which emerges from quantum mechanics. Then one of the pair particle can get into the event horizon, the other particle can escape. Then the surface, event horizon surface of the black hole acts as a black body. And the black body temperature, the so-called Hawking temperature, is inversely proportional to the mass of the black hole. In fact, I can tell you what the value of the temperature in numerical terms. The Hawking temperature of a black hole of mass m determined in grams is given by 10 to the power 26 degree Kelvin divided by mass of the black hole in grams. So immediately you can ask that suppose sun tomorrow turns into a black hole. Of course, sun will not turn into a black hole because it doesn't satisfy the Chandrasekhar criteria. But let's say you convert a sun-like object into black hole by somehow, then mass of sun is 2 into 10 to the power 33 gram. And what will be the Hawking temperature? 10 to the power 26 divided by 2 into 10 to the power 23 grams. It will be nothing but 0.5 into 10 raised to power minus 7 degree Kelvin. Okay, so therefore you can see a solar mass black hole is super cold as far as Hawking temperature is concerned. So most of the astrophysical black holes, because of this Hawking temperature formula, have very low temperature, and that's the reason Hawking temperature from no black hole has been detected so far. And because Hawking's prediction has not yet been verified either observationally or experimentally, that's the reason why Hawking never received a Nobel Prize. So in other words, to answer your question, if quantum mechanics is taken into account, then event horizon appears like a black body, slowly radiating heat, and the mass of the black hole slowly decreasing. And you can show that the age of a black hole, if the black hole is not accreting matter, if it accretes, of course, it will grow in mass. But if you have an isolated black hole, then according to Hawking's calculation, isolated black hole can lose mass due to Hawking temperature. But the age of such a black hole is proportional to cube of the mass. So age of an astrophysical black hole is very, very large, much larger than the age of the universe.
Thank you so much, Dr. Patrick Das Gupta. The next question is are there white holes? This question is by a student named Thanmay Mukamula.
Interesting question. So why did people think about white holes to begin with? Black holes, of course, as I said, from general relativity, you can show when matter is collapsing. If the matter is sufficiently massive, they will collapse to form a black hole where there will be a singularity at a point and covered by an event horizon. People immediately realize that After all, general theory of relativity, Einstein's theory, from which black holes are predicted, general theory of relativity is symmetric under time reversal. Like Newton's gravity is also symmetric under time reversal, meaning what? That if you capture the snapshot of a particle falling due to a massive object, then the opposite can also happen. That is, you run the movie backwards, then the particle, instead of falling, it can be going out of the object also. Because you have to reverse the velocity, and because time reversal symmetry is there not only in Newtonian gravity, it's also there for Einsteinian gravity. There is time reversal symmetry. So people said, well, if matter falls in to create a black hole, why not the time reverse version where from a singularity matter coming out? So the picture of matter coming out of the singularity is what is called the white hole. So from pure mathematical point of view, yes, white holes are possible. But then people like the Zeldovich's group, Novikov's group, long time back showed that although white hole is possible, but it's very unstable. Any disturbance of the matter coming out of the singularity, any disturbance will make the matter collapse to form a black hole. So in other words, although theoretically you do have white hole solution, but in real world, a white hole will be very, very unstable because there are always disturbance. It's like saying that if you take a pencil and a sharp lead of the pencil and you try to balance the pencil resting on the table on its sharp lead, then at no point of time you can have a pencil standing on its sharp lead. Although from Newton's motion, you know, if the center of gravity of the pencil is exactly vertically up in the direction from the point of contact, there should not be any torque. It should stand. But the point is, any little perturbation, the thing falls. So you can never have a pencil standing on its tip. It's unstable. There's unstable equilibrium. Similarly, although white hole is possible, but any perturbation makes it collapse into a black hole. So you will never see a white hole. If all these calculations are correct, you will never see a white hole in real life. But there are ways, there are theoretical ways to get around. You can always think of bizarre kind of matter which makes a white hole stable. And that's what theoretical physicists using a lot of mathematics, lot of ingenious ideas, they come up with all kinds of possibilities.
Thank you so much once again, sir. And so next we have a question on supermassive black holes. How do we, this is by Sanskruti, she asks, how do we know that there are supermassive black holes at the center of galaxies?
Yeah, as I said, that these are for the Milky Way galaxy. As I argued, for our Sagittarius A star, from the various eccentric orbits using some kind of general form of a Kepler's law, as you know, because these stars are orbiting so far away from the event horizon, you can actually use Kepler's law. And from Kepler's laws of the stellar motion, you can actually find out what is the mass. And the mass turns out to be more than 4 million solar mass. But you also see that the object comes very close to the center and as close as 20 billion kilometers. So you ask yourself, if you have an object whose mass is about 4 million solar masses, okay, and its size is less than 20 billion kilometers, what can it be? It turns out that no astrophysical object of such a large mass and such a compact radius can survive from theory all the singularity theorem of Penrose, etc., they show that it will collapse to form a supermassive black hole. So, to answer your question, Sanskriti, that the evidence for supermassive black holes are indirect evidence. That means you have used such observation and then asked what kind of an object can be so massive and yet so compact. From existing theory, we find that the only object would be supermassive black hole. But then, of course, the Event Horizon Telescope directly tells us, gives us almost with 99% statistical confidence level that you're seeing a black hole because you don't see any light from this central region. It is in agreement with the calculation that you have an event horizon, because from below the event horizon, nothing can escape.
Yeah, thank you, sir. Actually, Sanskriti also wants to know, like you explained how we know it is at the center of our galaxy, but she also wants to know how do we know that other galaxies have supermassive black holes?
Oh yeah, so that's a good question. So those are, as I said, that there are many techniques. So one of the techniques for active galactic nuclei is using hydrogen maser. People study, basically you have to study the motion of matter very close to the center. And for these quasar, active galactic nuclei, radio galaxies, what you do is you try to model, you try to find out what model can you have to explain such powerful luminosity, powerful jets. And when you do model, there are incredible amount of theoretical modeling has gone in, that by the spectroscopic observation of the radiation coming out of the accretion disk from the jets and all that, you can estimate what kind of supermassive black hole you have. So again, these are not direct deduction of a black hole. These are the black hole mass estimated by trying to model the observed radiation from the accretion disk, jets, magnetic field, and all that to find out what kind of supermassive black hole can lead to such a hot accretion disk. So for quasars, radio galaxies, blazars, you do a lot of theoretical modeling to estimate the supermassive black hole mass. So in other words, the estimation of the mass of the supposed supermassive black hole is obtained by trying to fit a host of observations with a theoretical model. By now, one thing is certain, that quasars, radio galaxies, active galaxies, they need supermassive. It's a black hole is a must as a central engine, because only for a black hole, the gravitational potential energy can be so negative that it can become hot. So because black hole is the most compact gravitational object, so that your matter swirls along, this cannot happen unless you have a black hole. So all modeling of quasars, blazars, radio galaxies, Seyfert galaxies, etc., they require a supermassive black hole. And supermassive black hole mass is estimated by detailed modeling of the accretion process, the radio jets, and so on, and compare it with the observations from radio, from X-rays, from optical, and so on.
Thank you so much once again, Dr. Patrick. So lots of students, many students are actually asking this question, that if there is a black hole in the center of the Milky Way galaxy, why doesn't it take the whole galaxy? And I think it was by two students, and one is asking, Parth is asking, can it affect our solar system or like solar system near us? So they are related questions.
Yeah, so of course, all matter that cross the event horizon will be swallowed by the black hole. That goes without saying. So yes, if this is your Sagittarius A star black hole, and this here you can see the photon sphere. The black boundary is the event horizon, while the bright ring is the photon sphere. All radiation which are close to the event horizon, and of course, if you cross the event horizon, then that cannot come out. You cannot come out. It's swallowed. But here are stars moving around far away from the event horizon, and conservation of energy tells us that matter which is moving, the energy is conserved, so therefore the orbit will not shrink. And of course, there is gravitational waves, but the rate of gravitational wave emission is so low that even within the age of the universe, these orbits will not shrink. And if it doesn't shrink and cross the event horizon, they are safe. Milky Way, our solar system is from the center of the Milky Way, is 27,000 light years away, far away from the event horizon. So we are very, very safe. The objects which cross the event horizon, they get swallowed. Otherwise, objects whose motion is maintained far away from the event horizon, they have no possibility of
Kanishka, and you touched about this a bit, and she asked on comparing black hole, the old one have.
So it all depends upon what kind of accretion disk forms around a supermassive black hole. So our Sagittarius A star doesn't seem to be having a hot, dense accretion disk going around our supermassive black hole, unlike what this cartoon picture of an active galactic nucleus. In order that you have a jet, you need a very dense plasma in which the rate of infall of this plasma into the black hole is very high. And if you have a dense plasma, any seed magnetic field as it differentially rotates will be amplified, and the magnetic field will have this kind of a helical structure. And as you know, the Lorentz force, V cross B force, will not let any charged particle cross the magnetic field, and therefore matter which enters this region, they'll be collimated in the form of jets. So therefore, only those black holes around which you have a dense plasma region with strong enough magnetic field and a high rate of infall, they happen to be active galactic nuclei. But there is also this correlation which I have alluded to, that the luminosity is correlated with the mass of the black hole. Okay, so as you have seen, that yes, our black hole, our Sagittarius A star black hole is only about millions solar mass. Black hole is too small to be active. So this correlation is bigger the black hole, higher is the luminosity, is due to something called Eddington luminosity, because Eddington luminosity tells us that you cannot accrete with a high rate of matter onto the black hole because the radiation pressure will blow the matter away. So the luminosity is directly proportional to the rate of matter in fall, and you need a more massive black hole to escape this Eddington radiation pressure, and therefore more the black hole mass is, higher is the luminosity. So it is essentially due to the radiation pressure which limits a small supermassive black hole as less radiative pressure and as less gravity to hold the accreting matter blown away by the radiation pressure, and therefore it can't accrete matter at a higher rate, so it will not be bright. While if you have a very heavy supermassive black hole, its gravity is high, so it can halt the matter blown away by the pressure of the radiation, and therefore it can support a very large rate of accretion, and thereby the luminosity will be very large. So to give a short answer, you're right. More is the mass of the supermassive black hole, more is the chance that it will be brighter. Our Milky Way galaxy is only 4 million solar mass object, and there is not enough matter near it, and therefore a bright accretion disk is not present.
Okay, thank you, sir. And the next question again is from Sanskriti, who is asking, what is the difference between accretion disk and the photon sphere?
Yeah, very good question. So accretion disk, as you can see, is matter falling in with angular momentum, and because angular momentum will not let matter directly go in, it forms a disk-like structure. Okay, and photon sphere is any photon. So there can be background photon. Of course, the accretion disk is also producing a lot of photons, but any background photon is present all around in a very symmetric manner. A photon sphere is a hypothetical sphere below which a photon trajectory is unstable, it will go into the event horizon. But above this hypothetical sphere, a photon can escape. It can go around the black hole and it can escape. So therefore, let's go back to the thing I just said as the photon sphere for the Sagittarius A star black hole. Yeah. So Sagittarius A star, even if it doesn't have an accretion disk, all the background photon, galaxy is producing so much background photon all around. These background photons, there is a region, hypothetical region around the event horizon. The background photons can move about without falling into the black hole. And the smallest radiation of such a hypothetical sphere where photons can go around without falling in is called the photon sphere. And all other photons, as you can see, from anywhere in the world, they are trapped. And sometimes some of the photons get leaked out and we see as some radiation around the event horizon. Okay. So I hope I have explained to you what a photon sphere is, and is different from the accretion disk. Accretion disk is the real matter, protons and electrons going around the black hole. And of course, when they are getting heated up, they will radiate photons. But the photon sphere is pure photon, just photons going around the black hole because of the black hole's gravity. And the photon sphere is the hypothetical sphere below which if a photon enters, it will not be able to orbit, it just goes into the event horizon.
Thank you so much, sir. And the next question is from A. Nanditha, She asks, how do supermassive black holes form from collapsing matter? Bose-Einstein condensate affects the formation of
This
galaxies.
is my research work.
Yes, sir.
This is a big puzzle as to how do you form supermassive black hole because some of these quasars from which you are seeing radiation took place when the universe was only 9 billion years 9 uh, million years old. You form supermassive black hole. There are many ideas, like there's a idea that the matter all around the center can collapse to form black hole, but all the ideas have certain loophole. The loophole is that you need a full spherical angular momentum to go very fast and not collapse to form a black hole. So, as a uh, solution, student myself and similarly Fazlur Rahman and myself, what we have done is we have shown that if dark matter particle happen to be bosonic particles but very low mass particles, that is the 10 minus 20 electron volts, then because they are bosons, the instant condensation can be simply explained as when the particle's velocity becomes very, very low, the de Broglie wavelength becomes bigger than the mean separation quantum system. And what we have shown is that dark matter particles which are having rest mass when include self-gravity, then let me not go into mathematical details. They can give rise to formation within very small time. Okay, so our dark matter particle bosons, and they have so low mass, 10 to minus less than 10 to minus 20 electron volt. Absolutely, we don't know. We don't know. So our theory you is verified. Very good. Your theory is turned out to be correct from experiments. Then you have to give up your theory. So what I'm saying is that if people indeed find that the dark matter particles than 10 to the minus 20 electron volts or in electron volt, mass in gram is about 10 to the minus 55 grams. Okay, so tiny mass. So in other words, what I'm saying is that if experimentalists find that dark matter particles are indeed bosons weighing less than becomes um, on the hand, you detect dark matter particles. More someone says is much more than 10 to minus 20 electron. Of course,
now we come to the asked by at least 5 related question is,
can you repeat the question?
students want to know, several students want to ask, can I also take a picture of Sagittarius A? And the students
So, it's a single is a very good question. Now, how do you measure small size object? So go back to your laboratory experiment. A tiny organism like a bacteria or a single cell, you use a microscope. What is the principle the microscope is using? The highest device is given by the formula is 1 point your optical device. Lambda is the wavelength. Whether you are using radio, optic, highest optical, highest angular resolution for any device you can have is obtained from the diffraction limit. It's the formula is 1.22 times wavelength diameter of the telescope or the microscope lens or whatever. So now let's take, you want to resolve the event horizon. Now, as I told you, it is 6.6 billion solar mass. 6.6 billion solar mass means 6.6 into 3, which is about 19.8. So take it to be 20 billion kilometers. Okay, you might say, oh, 20 billion kilometers is a very large radius for this object. 20 billion galaxies is at a distance of, you know, how much? 55 billion light years, not billion, 55 billion light years. So therefore, the angular diameter of the event horizon. So remember, the event horizon size for this is
Dr. Patrick, sorry, I'm interrupting. Just a minute. Actually, students are not coming, and Prachi is suggesting if you can.
Yeah. I don't know how it has become.
The voice is breaking, and students are not able to hear you.
Yeah. How do I
There is
increase the size?
Pardon, sir. There is speed test. You can do a speed test. I think all should be good. If the speed is good, your voice should go. If you can do a ask, sir. It can happen because of network. So if the network is good, the voice will be good.
I seem to have. Are you able to see me?
Yes, very much. And
are you able to hear me?
I am able to hear you very clearly.
Then how is it that others are not able to hear me?
I think it's okay now. I've got a report that your voice is coming now.
Okay, very good, very good.
Yeah.
So let's go back to this picture. So if you so let me go to that. Yeah. So this is the M87 black hole image. So as I said, that the radius of the event horizon for this is 20 billion kilometers, while the distance of M87 from us is about 55 million light years. So convert light years into kilometers, you will find that the angular size of this is so tiny that you need a radio telescope whose diameter is that of Earth's diameter to be able to resolve. Remember the formula 1.22 lambda divided by the D. So only D, which is the size of the telescope, if D is very large and lambda is sufficiently small, can you obtain the very good angular resolution. So do a simple calculation. Remember the formula 1.22 lambda divided by diameter of the telescope, and the fact that the event horizon size of M87 is 20 billion kilometers, while the distance is 55 million light years. 1 light years is about 3.26 parsec. 1 parsec is about 3 into 10 to the power 18 centimeters. So 1 light year is about 3 into 19 centimeter. So million so 3 into 10 to the power 19 centimeters means 3 into 10 to the power 14 kilometers. 3 into 10 to the power 14 kilometers and 20 billion. So 20 means 2 into 10 to the power 10 into 10 to the power 14. So 2 into 10 to the power 24 kilometers. So distance is 2 into 10 to the power 24 kilometers, while the event horizon radius is only 20 billion kilometers. If you 20 billion kilometers divided by 10 to the power 14, 10 to the power 24 kilometers, you can see the angular size is so tiny that you need, even if you take lambda, the radio wavelength, to be few centimeters, then you need the telescope diameter to be at least the size of the Earth. So the Event Horizon Telescope is a project where they use 8 different radio telescopes spread all around the Earth, and each telescope is viewing the object at the same time. They record it, and they are all compiled together. So it's a mammoth Herculean task, not only of actual instrumental challenge where 8 telescopes at the same time they're focused on the single object, but you are taking data and recording it with suitable time tag and do an enormous supercomputer data analysis. I'm sure after about few years, the entire team of Event Horizon Telescope people will be given the Nobel Prize, because it's a very, very challenging work. And I'm sure that they will be getting the Nobel Prize sooner or later. I hope I have answered your question. And of course, you can't yourself use a telescope. Your telescope will have the angular resolution so poor that you can't, and you can't even, with your telescope, you can't even see the M87 elliptical galaxy. Forget the black hole.
Yeah, thank you, sir. And I heard that the supermassive black hole at the center of our galaxy, it's like looking at a donut kept on a moon. So
yeah, exactly. Exactly.
Thank you.
It's like trying to locate a donut on the moon with your naked eyes.
Wow. So one of the students, actually 2 or 3 students have asked this question. What did we learn from this? What are the astronomers learning from the images taken?
Yeah, so the images are confirming the modeling of the supermassive black hole, which the radio galaxy people had modeled. So now the images are confirming that all the mass and angular momentum which was inferred from the model are correct, because the photon sphere, they bear the signature of the warped space-time geometry of the black hole. So a lot of modeling goes on to look at the photon sphere intensity. The fact that you are able to see this part, the gravitationally lensed image you are seeing. So you will be able to, in course of time, you'll be able to get details about the direction of the angular momentum of the black hole. This black hole is a rotating black hole, the so-called Kerr black hole. So details about the angular momentum will be soon found out, because you need more and more observations to make the image sharper. As you can see, the image still is not sharp. Your event horizon image is still not very sharp. So more and more observations are required, and over the years, these will be used to find out all details about black hole. Then in real time, how the black hole may be changing can be figured out, and so on. So these are the questions that astronomers and astrophysicists are interested. You might ask, how does it help mankind? Of course, none of the research in astronomy or astrophysics will help the mankind in near future, but of course, many spin-offs from research into astronomy has helped mankind. After all, your mobile phone has CCTV. You know, you take selfie or make your friend pose and you take pictures. How do you do it even in bad light? How do you get such a wonderful picture? Because your mobile phone has CCTV. These charge-coupled devices were actually developed by astronomers to look at very faint objects. So CCD is one of the things that was developed by astronomers, which today is being used in day-to-day life. Similarly, many of the techniques, the radio astronomy techniques, where the CAT scan technique, which is so important in medical field, they were inspired by the three-dimensional way of looking at an astronomical object. So although direct research in astronomy will not be having a direct impact on mankind today, but the spin-offs, while doing research for astronomy, several spin-offs come out of it, which come very handy in day-to-day life.
Okay, thank you, sir. Next question. Yeah, thank you, sir. The next question is by Shreyash And also similar question is by Kashika. They are asking, the Event Horizon Telescope was looking at the previous black hole M87 at the same time as it was looking at this one, the new Sagittarius A. Why did it take 3 years longer to capture the image of Sagittarius A? And
a very good question. Very good question. Yeah, because there are several challenges. Oh, you want to complete the question?
Yeah, no, sir. Your presentation is not in full screen, so I just wanted to let you
know. Yeah, so good question. So the point is that the M87 black hole is a very large black hole, and the event horizon, just now we calculated, is 20 billion kilometers. And as I said, matter goes around the black hole with almost light speed. So matter is orbiting around this black hole with speed of light, and you can find out what is the time scale of orbiting. Size is 20 into 10 to the power 9 kilometers. Okay, multiply by 2 pi to get circumference. Don't worry about this 2 pi factor. 2 pi will give you another 6 factors. So 6 into 20 will be 120. So 120 billion kilometers, and divide by speed of light. Speed of light is 3 into 10 to the power 5 kilometers per second. So you will find that the time scale over which matter is swirling about is days and weeks. While the Sagittarius A star black hole is much, much smaller. It is 4 million solar mass. So therefore, the event horizon size is only 12 million kilometers. 12 million kilometers, okay? 12 million kilometers is 2 into 10 to the power 7 kilometers. 2 into 10 to the power 7 kilometers divided by 3 into 10 to the power 5 kilometers. Okay? All right. So you can see that the time scales are few seconds. So the matter is swirling about the Sagittarius A star much rapidly, and therefore the image of the photon sphere is fluctuating on time scales of seconds, while the image of M87 photons were fluctuating over time scale of days and weeks. So therefore the data analysis was simpler for in the case of M87 black hole. Here, because the scenario, the picture is fluctuating so high, you have to carefully superpose, average, so that you take away the fluctuation, and finally you can get after taking out the fluctuation, you can get the this picture. As you can see, that the Sagittarius A star picture is not as sharp as the M87 because a lot of averaging has been done, and that's what the reason why it is slightly blurred. Is that clear? I think Vikrant.
Yeah. Thank you so much, sir. Yes, that answers another question also, actually. So I will ask you. The next question is. So actually, you asked. Okay. So I'll go to some more questions from the beginning. So yeah, one student was asking, and I like, which kind of technology was it photographed? Regular, optical, or infrared telescope?
No, it was radio telescope, because 8 radio telescopes at different parts of the world, so that you form a, almost the entire surface of the earth was like a radio telescope. And you had remember that formula, 1.22 lambda divided by d. So you are using a telescope of the size of Earth's radius. And that's the reason why you could resolve the small angular size both for M87 black hole as well as the Sagittarius A star black.
Okay, thank you, sir. And there is one student, Shaurya, who wants me to look up his question. So I'm just checking if I missed any question by Shaurya. Yeah. So, okay, actually, Shaurya's question is, let me see. Yeah, so he wants to know, can you see a black hole in a telescope and can you use spectroscopy to find distance of black hole? What is the scientific reason of black hole emitting pulsar? Well, I'm not sure.
Pulsar? No,
Yeah.
Pulsars are different.
Yes.
Pulsars are not black holes. Yeah, so what you see is not the black hole itself, because black hole from general relativity doesn't emit any light. What you see is matter going around the black hole, and therefore you can do spectroscopic studies of matter going around the black hole. In fact, spectroscopic studies give us lot of information, and that's how the quasar black hole masses are determined by using lot of spectroscopic data, both photometric data, spectroscopic data, the high time resolution data, because the radiation from quasars, they fluctuate. The X-ray, for example, X-ray radiation from quasars, they fluctuate in hours time scale. So you need really highly time resolved telescopic data that can do whole spectroscopic analysis over a wide range of wavelength. And all these data are used to model the black hole. So yes, spectroscopy is used heavily.
Okay, thank you, sir. And the next question is, one of the students is asking, which is the next black hole which we will image? It's by Siva Kumar S.
Well, the point is that these are the two black holes whose angular size was tractable. By the way, as a homework, you can find out what are the angular size of, I've already given the way to calculate angular size of M87 black hole event horizon and Sagittarius A star. You will find both of them are similar. So although the M87 black hole is 6.6 billion solar masses, while Sagittarius A star is 4 million solar masses, but because the distance is, Sagittarius A star is only about 27,000 light years away, while M87 is about 55 million light years away. So because of these distances, the angular size subtended here are roughly same. So if you want to find out black holes for other galaxies, if they are further away, then only if the black hole mass is very much bigger, you can do it. But that's the challenge. I'm sure the Event Horizon telescopes are trying to use more telescopes. Right now they are using 8 telescopes, 8 or 9. But by making use of much more number of telescopes, one would be able to have a effective large D, and then even further away black holes which are further away, they can be studied. But for a long time, I think M87 and Sagittarius A star, both of them will keep the Event Horizon telescope astronomers busy.
Okay, thank you, sir. So I'll just take the last question. Actually, there are so many questions, but due to the limitation of time, we can't take all. So I'll just take the last question. And this question is actually what happens. It's about colliding black holes. So this is by Thanmay Mukamula, and he asked what happens when two black holes collide.
Very good question, because as you know, the other instrument, namely LIGO and Virgo, gravitational wave detectors, they have already seen inspiraling black hole binaries. So when two black holes, if you just take two black holes with no matter around it, then they will not be emitting electromagnetic waves. But if two black holes without any matter around it, they are inspiraling because they are going around each other. General relativity predicts that they will emit gravitational waves. And as they emit gravitational waves, they will lose energy and further spiral close to each other. And finally, they will just coalesce into one bigger black hole. So in fact, those who remember, the first direct gravitational wave detection was about two black holes, one weighing 29 times sun's mass, the other 36 times sun's mass, and they coalesced to give rise to a bigger black hole, okay, which was about 63 solar mass. So 29 plus 36, how much?
29 times 36. I need to
29 plus 36. 29 plus 36 is 65. So, but the black hole which was finally formed was only 62 solar mass. Where did the 3 solar mass go? It went away in the form of energy and be radiated by the gravitational waves.
Wow.
So, to answer your question, two black holes, when they come closer, they become a bigger black hole. But there is a area theorem by Hawking. The area theorem says that in any process, the net black hole's event horizon will be always larger than the sum of the individual event horizon area. So, in other words, if you take two black holes and calculate the event horizon areas for both of them, let's say A1 and A2, when they finally become a bigger black hole, the event horizon area of the bigger black hole A will always be greater than A1 plus A. That's called the Hawking area theorem and is related to black hole thermodynamics.
Okay, so thank you so much, sir. That brings us to the end of the Q&A session today. We had a wonderful time.
Thank you.
And, so we learned a lot. And I would once again like to thank Dr. Patrick Das Gupta for joining us and igniting the fire of learning inside all of us.
My pleasure.
Actually, there were so many questions, students, but due to limitation of time, I think we could only take a few questions. And thank you so much once again for all your questions. And I'm sure all our students truly benefited from the interaction. And I want to thank all the students for joining today. And also would like to thank the space team members behind the scenes for making today's interaction most successful. And truly, I'm today, once again, I felt really honored to be here representing space. So thank you so much. And
the questions were really very good. So I advise all of you to, follow up by making simple numerical estimates. And, science always relies on quantitative estimates. So you'll get a good practice. If you just do just simple numerical estimates, you will understand much more.
Okay. Yeah, sir. That reminds me that thank you so much, sir, for that wonderful message. We will keep in mind and encourage our students also. And that also reminds me, Dr. Ratnashri used to tell us a lot about, I think your voice is breaking somewhere.
Really?
No. Yeah, so she used to tell us always to derive numbers from nature. So this wonderfully reminded me of her. So with that note.
Yes. In fact, this is my first interaction with the space online. Yes, and I dedicate this to my dearest wife Ratnashri, who sadly COVID snatched her away last year. And I dedicate this, my interaction, to my late wife, Dr. N. Ratnashri.
Thank you so much, sir. That's an apt dedication in our memory, who has been such a good mentor in space. And you have also been supported space always. So thank you so much. With
my pleasure. My pleasure. So all the best to you, Prachi, Sachin Bamba, and all the students. My best wishes to everyone.
Thank you so much, sir.
Most welcome. Most welcome. Take care, and I will now. Goodbye and good night.
Yeah, thank you. Goodbye and good night, sir. And we will meet you, Megha and I. Maybe some space members would also like to come. Prachi, so the webcast is off, I believe. All right.